Very good afternoon, good evening to you all. So I welcome you all to the fifth session on this series, geoprocessing using Python. We are sorry for the delay. So when we will start. So actually in the last lecture, we learned about how to write a raster using GDAL. So for writing a raster, first you need to create, like there are two options. One, either use create copy or use create. So create copy, whenever you already have some existing data in the raster format and you wanted to do some processing or some modification on the data. And with the help of create copy, you can just copy everything from your uh, existing raster, like the number of bands, projection, transformation information, everything is copied. Then later on, you can just modify some of the data there and write it back. So this was the create copy. Then using create, so suppose you have data in some other format, like you have collected data from the field, but that data is raster, but you have saved in some CSV or some other format. So for better visualization or distribution, you wanted to convert it to the raster format. So in that case, you have your create was the better choice. So with create, you need to know like how many bands you are going to write, so how many pixels are there, and so on. Plus, then after once this is done, then you need to create a projection system. Suppose if you want to store projection information, you need to create projection, and you just with set projection at set geotransform, you can just write those information. Plus, you can attach some metadata also to your raster. So this was just about writing a file. Now today we will discuss about stacking raster. So generally what happens when you download images from any service provider, like if you are downloading the data from Bhuvan or NASA's website or even ESA Copernicus, what do you get actually for every band? You get a different image. So suppose if the satellite or your data is in some 7 bands, so you will get 7 different files. Now suppose if you want to visualize the composite raster, like out by combining red, green, and blue. Suppose you want to create so now a true color composite or true color composite of your image. So we will learn now how do we combine multiple single band images to create a composite colored or some standard false color composite or some true color composite. So I have in this, I will show you first. I have in I have here in this folder, I have 4 files. So these are 4 files of list three payload. Four files actually, one band 2, band 3, and band 4. So we will combine these 3 bands together to make a standard false color composite. So band 4 is NIR, band 3 is green, and band 2 is red. So we will combine these three files together and make a standard false color composite for list 3 image. So anyway, first what I am doing here, so anyway, first I have created a list. Like what we will do, so we will go over all the files together. So file names I have stored in a list. So this my list contains three file names. So now what I am doing here, for file in file names, so I am iterating over all 3 files one by one. Then what I am doing, I am just first opening the file for reading. So ds equal to zidal.open, then I am passing it a file name, and actually this argument is optional. Otherwise, by default, it will be read only. If you don't want to skip it, you can skip it as well. So ds is equal to zidal.open and pass your file name. Then what I am doing, then I am just reading the data from that. So either directly you can fetch some particular band, like you can do band is equal to GDAL dot raster band, or directly even you can call it reader, because it's a single band image I know already. Otherwise, if this is a multi-band image, and suppose your image itself directly is multi-band and you just want to extract some particular band from that, then you can do this. So So get raster band, whichever band you want to fetch, get raster band, and then band dot read as array. So once this is done, I will get a two-dimensional NumPy array from this. Then what I am doing, I am appending this NumPy array to my one new list I have created here. So actually, whatever code I am showing, this may not be the as I explained earlier. Also, this code may not be the most efficient way to write the code. So this is just for demonstration. So there actually you can write it in different ways as well. But this is just for easy explanation. I have written it as a simple loop. So in this so this way you can, suppose if you have more than 3 bands also, you can combine together 4, 5, 6, 7, 8, 9. So the advantage of this approach is this. So once this is done, then what I am doing, I am storing this every two-dimensional NumPy array into a image data array. So now if I run this code, now if you see image data, img data, so this is a list with 3 elements. Now you can see that img data is a list with 3. It has 3 two-dimensional NumPy arrays in this. So you could have created a 3-dimensional 2D NumPy array also by combining these by stacking together. But anyway, for simplicity, I have assigned it to a list. So these are 3 different arrays in this list. Now, for stacking the band, now suppose if you want to visualize these all together, so I have created a figure of this size. Then I am going over this for I in range 1 to 4. Then subplots. So 1 row and 3 columns I have arranged. 3 subplots I am going to create. And in every ith or ith plot, I am just plotting this img data I minus 1, because here I is starting from 1, so I am subtracting I minus 1, because in my list the indexes will start from 0, so I am just subtracting 1, I minus 1. So this way you can visualize like slight difference you can see between the bands. So this is red, green, and this is NIR. So now let us see how do we create a how do we combine or make a composite from this. So now what I am doing here, I'm just giving it a destination file, a name like rgb.img.tif. If it is existing in my drive, I will just delete it. So anyway, it is not existing in my drive, so I need not delete anything. So I'm creating. So then I am just querying like from data.shape, what is the width and height of my image. So if I print it height and width, you can see that 1151 by 1151. So because this data I need to create a driver or what a data set. So first thing, like now, because our data is available, so this is similar to using a create. So in create, so in earlier version we saw that we were just creating a single band image. Now we have to create a multi-band image. Anyway, now data already we have in the form of NumPy arrays. So now we can just create a destination data set and write on that data one by one. So the first thing what I have done here, I'm just creating a driver. So as explained yesterday or in the previous lecture, driver jidal.get driver by name. And then pass it the name of your format in which you want to write your file. So suppose GTIFF or IMG or JPEG 2000 or whatever format you want to create. So jidal.get driver by name and name of the format GTIFF. Then once the driver is created, then you need to pick up the function driver.create. So drv.create. So you need to pass is the name, destination file name, in which file in which you want to write your data, width of your image, pixels, and height of your image. So height is 3. And no, not 3, sorry, 1151. Then number of bands. Now because we are creating a composite of 3-band composite, so we are passing number of bands 3. and E type is the data type. So data type is, so here actually in our source file itself, the data type is unsigned. So every pixel is stored in unsigned 16-bit integer. So the data type is GDT uint 16. So uint 16 means it's a 16-bit unsigned integer. So once the data set, destination data set is created, so now suppose you want to write projection and transformation information also, if you want to wish to attach to it, destination data set dot set projection, because all three images are from the same sensor, so their projection, so we are assuming here that the projection and transformation information in all the images is same. So what I am doing, I am assuming here all have the same projection and transformation. So I am just copying the transformation information from one of the data sets. So here you can see DS. I just opened here. My DS will be the last image which I have opened. So I am assuming that in all the three images, the DS and the projection and dual transform is same. So I am writing this only as the transform of the my entire false color composite. So destination dataset dot set projection. Now I am getting the projection from DS. So DS dot get projection from the source image or band. Like this will be last band's image. Dot get projection. I am getting the projection information and copying it to the destination dataset. Similar with geo transform, I am getting from the DS or my source image and copying it to the destination. So once this is done, so everything is done now. Destination data set is created, projection and transformation information is written to it, and basic information like its width, height. So the data is ready in the memory. Now what we need to do, we need to write the NumPy arrays or data into it. Now a framework is created already. So it must be filled with zeros. Now we are going to write the data. So for writing the data, same thing as we have done in the previous lecture. Now, because this is a three-band image, as I explained yesterday, that band indexes in GDAL starts from 1. Generally, in the other like arrays or lists, the indexes start with 0. But in case of GDAL, the band indexes start at 1. So we'll be starting our loop from for I in range 1 to 4. So first thing, from the destination data set, we need to fetch the particular band in which we want to write the data. So anyway, we will be looping over one by one, band 1, band 2, band 3. So in this loop, destination data set dot get raster band I. So first it will fetch the band 1, then band dot write array. So image data I minus 1. So as we have seen in the previous portion of this code, so we were reading these three files one by one and storing the read data into a list called image data. So anyway, image data is a 3-element list. So in the band 1, we are writing the data from the zeroth element of the list. So band dot write array image data I because we are giving here I minus 1 because GDAL indexes are starting from the 1, but our list index will start from 0. So for synchronizing them together, so in IMG data we are passing I minus 1. So once this is done, so all data will be returned to the destination data set. So once this is done, we need to call the flush cache. So with the help of flush cache, all the RAM elements will be written back to the disk. So if we don't call the flush cache, what happens? Operating system for optimizing the performance, operating system may buffer the data for some more time and write it back to the disk on some later time. And suppose if you open that disk, the file will be created. So if you open that file with some GIS software or even with Python itself, so you may be seeing some black image. So what might have happened there? Because you have not flushed the cache, so actual contents may not have been written yet to the disk. So just by calling this flush cache, we are forcing the operating system to write the contents to the disk. And destination data set equal to none means we are freeing the destination data set memory associated with this. So we are freeing the resources. Here now we can see that this way this So here an image must have been created if you see here. So where is my folder? Enormous Haridwar. Then L3H44. L3H44 21 421. So in this here you can see that RGB img.tif. So suppose this image you can open in some other software as well, or we can. So I will first once again I will, otherwise I will delete this image. Write the code once again. I am just deleting this file and just executing the code once again to confirm that this file only was written. So RGB img.tif has been created. So with this code, a 3-band image got created. Now let us read this particular image back and see that everything has been written correctly. So this way we can see that for stacking multiple bands together to create a composite image. So similarly, like we need to read the individual, we need to read the images one by one, store their data in some list, or actually you can create an array itself. So store that data temporarily in some array, then create a driver for writing your format, like format driver which will be handling your format GTIF or IMG or JPEG 2000 or even NVGDAL format, whatever you want NV format. Then once the destination data set is created, then you need to create a destination data set. So destination data set, you need to pass the arguments, your destination file name, number of pixel width, height, and how many bands are in your composite image, and the data type for each pixel intensity. So once this is done, then you can loop over all the bands one by one and write the data into that. This is done means then you can copy projection, or you can create new projection system, whatever information you have, create projection transformation, write it to the destination data set and write it back to the disk. So these are the basic steps for creating a composite. Now let us see that whatever we have created, is this correctly? Are we able to read it properly? So anyway, destination file, this we have created a composite called rgbimg.tif, and the variable name is destination file. So now I will just read this back again from the disk. So didal.open, and I'm just reading it back. So actually I just restarted my kernel, so it is not able to hold this variable. So I need to just run these all again. So here I have just read the file. So then I'm just, so actually now I'm not interested in individual band one by one. So I am just reading directly on the data set. I am calling read as array instead of fetching bands one by one. Directly I am just calling read as array on the data set itself. So it will return me in a 3D array. So data. So just for visualizing, I am just rearranging the data so that matplotlib can plot it. So I'm just destacking, then I can see the data. So this way, we have created the false color composite by stacking 3 individual bands together. So here you can see that this doesn't look like a standard false color composite because the ordering of the bands might have been different. So we will see that how do we order bands together so that suppose the band which you want to be displayed as red goes to the red band 1. The band which you want to be displayed as green goes to the green, and band which you want to be displayed as blue goes to the third band only. So actually an image can have multiple bands, but for visualization you can select only 3 bands so that with the combination of 3 bands it so false color composite you can see. So now we'll see that how do we reorder the bands so that the indented band goes to that particular band. Like suppose you want band 7 to go to the red, or band 8 you want to go to the red place. So that way, let us see that how do we rearrange or reorder the bands to get the false color composite of our interest. So this is done, and this way, so we can stack the bands together. So let us see that reordering. So for reordering the bands, we will use Jidal has a utility called translate. So with the help of translate, you can reorder the bands. So generally what happens by default, band 1 is interpreted as red, band 2 green, RGB. So band 1 is interpreted as red, 2 as green, and 3 as blue. So now our source file is RGB img.tif. So if you go about this Jidal.translate, so if you read Jidal.translate takes these following arguments, like first is your destination file name or output dataset name, then your source dataset in which you want to rearrange. So that can be, see actually output it takes a destination dataset name and source dataset is a dataset or file name. Then there it can take multiple arguments, like if you want to show the options. So here you can pass multiple other options like format, output type, like band list, and if you want to mask particular band, you can pass width percentage, like height percentage, resolution, because you can change the resolution of output image as well, and you can tell about the projection information, RGB expand, so many resampling algorithms. Suppose if you are resampling the image and so on. So here what I am doing, so I'm just calling Jidal.translate and I will store it in the new file called name rgbreorder.tif, and the source file, anyway my source file is rgbimg.tif, and band list as 321. So what I am doing here, I am creating like band 3, whatever I have in my source image, whatever band 3 is there. So band 3 I want to put it into the red position, and band 2 I am pushing it to the green, and band 1 I am pushing it to the blue blue band. So this way I am just reversing the order of their sequence. So this way you can change any order, like now. So this it returns us a data set. Once Jidal.translate, it is writing to this file rgbreorder.tif, and you need to pass it your source file and band list in which order you want to arrange the band. So here band 3. So first argument whatever we pass to this band list will go to the red, and second will go to the green, and third will go to the blue. So we wish to push band 3 to the red band 3 to be interpreted. You can take it as band 3 to be interpreted as red, band 2 as green, and band 1 as blue. So once this is done, just this I am rearranging this for plotting by matplotlib. So data. If I see here now, this we have created a standard false color composite. So this image itself, if you reorder the bands, you can see you will see a different image. Now suppose let us see how I change the band list, band order in some different order. Like instead of 3 to 1, that was 2, 3, and 1. So this way you can see a different false color composite. So just by calling a simple command gdal.translate, you can rearrange your bands. Like 3 and 1. And so this way with just gdal translate, you can reorder your bands. Now let us see how do we subset a raster image. So this requirement also sometime may come because you have a very large image and you are interested only some particular subset of that image. Now, as explained in my previous lecture, subsetting you can achieve in two ways. So once you know that their pixel, the coordinates in pixel coordinate system, like their pixel number, like you are interested in the image, this pixel number and this line number to this pixel number and this pixel number, this line number. But in general, sometimes you may be knowing the coordinates only. Like suppose if you know the coordinates of, you have the entire image of entire Uttarakhand, but just you want to clip the for Dehradun region only. So you know the coordinates or four corners of the Dehradun in terms of latitude and longitude. Now you have this information only. So you just from your big raster, you just want to clip this particular area only. So you'll see that how to subset a raster. So when you this same image band to image, we will subset. So anyway, I have created a variable called file name in that stored the name of this file. I am just opening the file. So first thing I am just getting the affine transformation information of this image by calling ds.getGeoTransform. So if I run this anyway, if you remember it, so GT will be a 6-element tuple. So first is the coordinate or longitude of 0th pixel. This is the resolution in x direction, and this is rotation in x direction. If this is 0 means north is up in our image, and this is the latitude of our 0th pixel. Then this is the rotation in y direction, and this is the resolution in y direction. Now this way, by applying this geotransform function, we can calculate the latitude and longitudes of four corners of our image. Like this, you can see that. So this particular image is covering this much area, 77.99 degree north and 30.00. So this is the upper left corner, 77.99 and 30. This is the longitude and 30 is the latitude. And the lower right corner is 78.25 to 29.7. So our image is covering the area from 77.99, 30.00 to 78.25 to 29.74. Now suppose if you are interested only in these extents, so these are the extents of our image, like this is the minimum x. So latitude varying from 78.15 to 78.20, sorry, longitude from 78.15 to 78.20 and latitude from 29.75 to 28. So 0.5 by 5. So we are just interested in 0.5 degree in the x direction and 0.5 degree in the y direction, starting from 78.15 and in the latitude direction 27.95. So I just created a list with 4 elements. So these are the 4 corners, or what you call upper left and bottom right corners of my image or area of interest. So now first thing what I need to do, I need to convert these latitude and longitudes to the image coordinate system. So from this latitude and longitudes, I need to convert like which image, which pixel number and line numbers cover these area. So I am first creating an inverse geotransform. Here I was applying geotransform. With just geotransform, what I was doing, with the help of geotransform function, we can convert line number and pixel numbers to the real world coordinates. With the help of inverse geotransform, we are converting latitude longitudes to the line number and pixel number. So I'm just creating a variable for GDAL.inverse geotransform and passing it the geotransform information. So GT I am just passing, GT was ds.get geotransform was my GT. So by this I will get a reverse or inverse geotransform. So now if I apply this same, like apply geotransform and I pass this instead of GT, I am just passing it inverse GT. So offset equal to inverse GDAL.apply geotransform, inverse geotransform, and I'm passing it like my extents. So first these are my extent 0 is my uh, top left's longitude, and extent 3 is top left's latitude. So for these four corners, I am for like my top left, I am calculating what is the line number and pixel number. So with offset, suppose if I get the offset 2 numbers, I will be getting here. So offset, if you see, so this point like 78.15 and 29.75. So this is the corners of my image. So 78.15 and 29.75. So this is X and Y. So corresponding to this latitude and longitude, these are the line number and pixel numbers. So actually this is giving me some floating point numbers. So actually in the image, these will be like integers. So I have to convert these floating point numbers to integer numbers, because actual my offsets will be in integers. So I am calling here map function. Map will be iterating over this list and applying this particular function to all the elements on the list. So either see, you could have gone one by one to these elements, or you can call directly the map function. So map function, what it does, it applies this, it takes two arguments. One is the function to apply to. So int is a function here. Like suppose if I give int 6.7, int 6.7, what does it do? It converts 6.7 floating point, this number 6.7, to an integer 6. So here what I am doing, offset has returned me a two tuple element, so in which these numbers are floating point number. So map, I am applying integer function to the every element of my offset tuple. So offset is a tuple or list here. So with map function, I am applying integer. So either I could have written a loop for a in offset in this, or directly I could, in a single line, I can write like map applies this function to the all elements of this offset list. So then anyway, this is a two tuple list, two element list. So if I unpack it, it will return me a tuple. If I unpack it, I will get two variables like X and Y. So I am assigning these to two variables, X of and Y of. So this is, so now you can see offsets was 686.600 and 908.80. Now after converting it to integer, it has become 686 or 908. See, actually for just two elements, I could have written with two lines also. But when you have multiple elements, or you are going to do it multiple times, so at that time this map function will be convenient. So this time it might not be giving any advantage, but when you have bigger list, then it gives definitely advantage. So now I have converted these coordinates 78.15 and 29.75 to the line number, pixel number and line number in my image coordinate system. So there are 686 and 9. Similar way for the bottom right corner. Bottom right corner also I need to do the same thing. So again here I am calling like this offset 2 and apply geotransform, inverse geotransform, and this is the longitude of the bottom right, and this is the latitude of the bottom right. So if I say, so now I have to subtract, so I have to subtract from 686,908 to 908,1131. So now I can, with this, I can calculate how many rows of the data I have to read. So how many rows means my y offset 2. So my bottom right, whatever the line number is there, minus line number in my top left corner. So this way I can calculate how many rows I have to read. And by subtracting my x offset to x offset from my x offset to, I am calculating how many columns I have to read in the image. So this way, in this area, how many rows and columns will be there. So that information I am calculating by subtracting these two values. So if I see, I have to read 2 to 3 rows and 2 to 2 columns. So as explained in the previous lecture also, suppose if you call ds.read as array without any argument, so it will read entire image or entire array. Then you can pass some more arguments to ds.read as array as well. Suppose if I see, so like you can pass it on like x offset, y offset. If you don't pass them, it will be 0. Then x size, how many rows or columns you want to read, like x in x size, how many you want to read, and y size, then buffer, and all this I will be covering in the next slide. So data equal to ds.read as array, x offset from which offset you want to start reading your image, y offset from where in the y direction. Similarly, how many columns you want to read and how many rows you want to read. Anyway, this all information we have calculated x off and y offset. So these are 686 and 908. So we want to start from this location. And anyway, number of rows and columns, how many we have to read, that we have calculated already. So it doesn't take like x offset 1, y offset 1, then x offset 2 and y offset 2. But instead of that, because it takes how many rows and columns from starting from this point you want to read it. So we have calculated this information. So if we read this data, so if I print the shape of this data, so it should be 223 by 222. Here you can see that this data is 223 by 222. Now suppose if, as I showed, if I just read it entire array, it will read an entire image. So if you pass on some more arguments, then you can read some particular subset of your image itself. Now if you want to visualize it, so I'm creating a 1 row and 2 column plot. In that 2 subplots I am creating. In one, I will be this ds.read, the entire image I am plotting, and another I am just subset of the image I am. So here you can see that this was our entire full image, and this is our subsetted area. So this is 1151 by 1151. This is 231 by 222. So this somewhere here, this area we have just subsetted. So this way we can subset an image. Now, suppose if you want to write this image to some other file, because just subsetting will not have you, because when you are this is for visualization. Now you may be doing some processing on this and writing back the result to some other file. So now what we need to do, because when suppose if we use create copy, then because the extents of our image has changed, so we need to write because the projection has not projection information has not changed, but our transformation information have changed. So suppose if we use create copy, so in create copy, what will be geo transformation information also will be copied, plus number of rows and columns, everything will be copied. So here what we need to do, we need to calculate the transformation, and anyway the projection we can copy from the source image itself, because the projection information will be same, and write data already we have, and thus we can write it back. So what I have created, I am just like copying the geo transformation, because other information is same, only our coordinates of x0 and y0 only have changed, because we have not changed the resolution, neither we have changed the resolution, nor we have rotated the image. If we are going to do that, Then we need to create another 6 tuple element filling those values. But anyway, we have just changed the coordinates of our 0, 0th pixel. So I am just copying the detail element as it is, and 0th and 3rd element, just these 0th and 3rd elements, I am changing or assigning it the new values from this sub extents. So that's all what I'll be changing. Now if we see, this is our new transformation information. So x0 is instead of 70, earlier this GT was 77.99. Now it has become, because our image has new coordinates 78.15 and resolution remains same, rotation remains same, and this y well, what do you call y0 or latitude and other things are remaining same. So now same thing, like we are creating here we are, what we are doing, we are just chaining two functions together. So gdal.get driver, so gdal.get driver by name geotiff, if then on that itself we are just calling create. So we are chaining another method instead of assigning it to a variable, then on that variable calling another function. Instead of that, we have just called them all together. Gdal.get driver by name, then create subset.tif. Anyway, here we know that how many columns are there, we have calculated, rows calculated. This has single band, and data type we are not passing it up, but it will take a default data type. So once this destination data set is created, so just now set projection, and we are just copying the projection from our original data set ds.get projection, and set geotransform. Geotransform, we are writing the new transformation information because our origin coordinates, origin pixels, 00 pixels coordinates have changed. So we are writing these new coordinates. So GT subset, whatever we have created, this is done. Then get fetching the band one from our image, because this is a single band image, or we are writing single band. So get raster band one dot write array. In data we have fetched the subsetted image and writing the array. So write array. Then once this is done, we are just flushing the cache and deleting this destination data set. So this way we must have created see in my folder a file with name, what was name I have given, subset file subset.tif. So a file with name subset.tif must have been created here. This is the folder LHF496350. So a file with this name must have been created, but I need to check my current working directory. So the file must have been created somewhere here. Okay, raster RGB reorder. So we're going to subset.tif image with name subset.tif got created here. So this way you can subset your image. So once this is done, now let us see how do we resample a raster. So resampling a raster means changing the spatial resolution of a raster data set and set rules for aggregating or interpolating values across the new pixel size. So sometimes what may happen, you want to do some analysis on two images, but both the images have different spatial resolution. So because for applying some operation on the both combined images, like you want to add two images together, or you want to get the maximum or minimum. So if both the images have different spatial resolution, because for applying some algebraic operation on the both the images, like the size of the both arrays must be same. So for that, what you will do, you sometimes you will, or suppose because your data may be, so you may be combining data from different sources and their spatial resolution may be different. So for doing some analysis, you need to bring them to the same spatial resolution. So resampling is the process of aggregating the data. So or no, actually changing the spatial resolution of your image plus the rules for aggregating, because what might happen, you might be bringing some or breaking the big cell to some smaller cells, or you may be aggregating 2, 3 or 3, 4 cells to a single cell. So resampling is these changing the resolution plus the set of rules for aggregating or interpolating. Like because when you are breaking a bigger or a higher or coarser resolution cell to a finer resolution cell, so you will be getting new pixels. Now you interpolating the values for those newly created pixels, or when in case you are aggregating like multiple cells to a single cell, then aggregating the values of all those pixels to make a coarser coarser pixel, you need to some set of rules. So those are called the sampling techniques. So there are multiple resampling techniques like nearest neighbor, bilinear, cubic, and there are multiple more. Actually, nearest neighbor is one of the easiest resampling technique. So like here you can see that this was our a final resolution image. So here what we are doing, we are aggregating these four finer cells to a big coarser cell. So now how do we calculate the value of this bigger pixel? So we may calculate the mean of these all 4 pixels and assign the value to this bigger pixel, or mean, max, or you can take standard deviation, or sometime what may happen, you can do it in reverse order as well. You may be breaking this bigger or coarser resolution cell to 4 smaller resolution cells. No, now this resampling technique will tell you how to calculate the values of these 4 smaller pixels. So for example, here you can take that like you maybe in the nearest neighbor technique. So here this was we have initially 3 by 2. This is our image, we having 6 pixels, 3 columns and 2 rows. Now we have just created 4 smaller cells from this bigger cell. Like we have copied the 68 value to these all 4 pixels, or 70 value to these 4 pixels, 69 to these 4 pixels. So this is the nearest neighbor sampling technique. Here we have gone from coarser resolution to the finer resolution. Or this way, like here, same thing like this. Now these, what we have done here, we are aggregating the pixels together. So these 4 pixels has been aggregated to a single pixel. So 68, 70, 69, 69. This maybe we have taken the average of these 4 pixels and assigned the value to this bigger pixel. So similar with these 4 pixels. So either we can down sample or up sample. So then how to calculate the values of aggregation or interpolation will be based on the resampling technique we have selected. So let us see how do we do a resample an image. So first thing, we are just opening a file. Anyway, I have assigned to file name some variable, file name variable some name anyway previously as well. So now I am just fetching band 1 from this image. So like band.read as array, if I call band.read as array, it will read me entire array. This I will call original data. So the shape of my original data is 115 by 1 by 1151. Now I will see that how do we resample this image. Now first what we are doing, we are creating from this coarser image, coarser is spatial resolution image, we are converting it to a finer resolution image. So just we are converting, we are reducing the size of our pixel, or like whenever there were, so this 1 pixel we were breaking it into the 4 pixel. So similar way, now here what we are doing, our original size of our image was 1151. So in the same extent we are creating now 1151 by 2 into 2. So we are just doubling the pixels, or we are reducing the size of our pixel. So now in the same extent the number of pixels will be double. So with that, what we are trying to enhance the spatial resolution of our image. So how do we do that? So in the band.read as array, so in the same function is used for resampling as well. So band.read as array is what you can call as generic function. So it can be used for subsetting the image or even resampling the image. So band.read as array, and if you pass it two variables, one is called buffer x size and buffer y size. So buffer x size tells you like whatever number of pixels you have read, so in how many other pixels you want to resample. So if, because we are reading an entire image, and buffer x size we are passing it because in our original image there are 1151 pixels. So what we are doing, we want to buffer these pixels into 1151 into two number of pixels. So same pixels, or whatever pixels are there in our original image, so same pixels now we want to break into, say, to double the, we are doubling the number of pixels, or we are reducing the size of pixel. So 1151 into 2, same way buffer y size also 1151 to 2. And resampling algorithm, we can pass that to, there are multiple algorithms. So GDAL if you call GDAL.gra underscore, then there are multiple algorithms. So we are calling bilinear. So with the bilinear resampling technique, we are resampling to a finer resolution image. And similarly, suppose if you want to convert it to a coarser resolution image, same function we need to call band.read as array, but instead of buffer size x, now buffer size now we have reduced to 50. So 1151 pixels we are aggregating to just 50 pixels. So in the final resolution type, we were incrementing, 1151 pixels, now we were fitting into 1151 into 2 pixels. So we were we are doubling the number of pixels. So what will happen? The area is same. If we are doubling the number of pixels, the size of pixel will reduce. Here in the second case, what we are doing, we are aggregating. So multiple pixels will come. So 1151 pixels we are aggregating into 50 pixels. And here resampling technique we are passing nearest neighbor. So the argument resampling underscore algorithm equal to whatever you pass, GDAL.gra nearest neighbor, or GRA bilinear or bicubic. This way you can resample your image. Now let us visualize these all images together. So this was our original image. First plot is our original image. So here you can see 11511 by 1151 size, and this is final resampled image. So here you can see the number of pixels. So the same extents, but the number of pixels has doubled. So this way our see actually we are not, by just resampling the image, we are not adding any extra information. So with this we must not expect that the some information content in your image we are not increasing. We are just increasing the number of pixels or compatibility with other image. So it is not going to enhance our image in any way. Because with resampling we are not adding any extra information to the image. We are just adjusting the number of pixels only. So here we can see that this is the changed image. We will not see much difference between these images. Here we have aggregated into just into 50 by 50 pixels. So here you can see that, simply see the changes. So now the image looks quite discrete image. It looks quite discrete. So this way we can resample our image using a read as array method. So once this is done, we can close. So then you can select the sampling technique based on your requirement. Now let us see that how do we reproject an image. Reprojection requirement also comes like when you have data coming from different sources. Some are in geographic coordinate system, some are in projected coordinate system, and you have some vector raster, all data, but all the data have different projection systems because they are coming from different sources. So you want to do some analysis on them. So before doing the analysis, you need to bring them to the same projection system. So then only your analysis will be correct. Otherwise, you will get some garbage results. So this is for for bringing some different projection systems or the files in different projection system to a common projection system is called reprojection. So here now I have a image here like this, and this is some DSM image. So now suppose I want to reproject it to some projected coordinate system. So first thing, I am creating a projected coordinate system as explained in my previous lecture. So there we just created a geographic coordinate system. Here we are creating a projected coordinate system. So for creating a projection system, first you need to call OSR.spatial reference. So OSR.spatial reference creates a projection system. Then we are calling the CRS.set projected coordinate system, because this projection system we want to create as a projected coordinate system. So CRS.set projected coordinate system, and we are creating a projection system called UTM. And then there is a function called on UTM, set UTM, like which UTM number. So UTM 44, and by default it will be north. Otherwise you can pass another argument whether north is true or false. So by default north is going to be true. So the projected coordinate system which we are creating is here 44 UTM 44 north. And on this we are setting the GeoGCS or coordinate system at WGS 84 or datum WGS 84. Now suppose if I want to see this projection system how it is. So it says this is projected coordinate system, and a geographic coordinate system attached to it is WGS 84. So this is the projected system for WGS 84, and these are the details of this UTM 44 north. So UTM degrees, and this is UTM. Now this I have created a projection system. Now I want to reproject my image to this projected coordinate system. Now anyway, first I am reading my file gdal.open. I am reading my data set. Now there is a function in GDAL called GDAL. Actually, either you can call GDAL.reproject or you can call GDAL.autocreate warped VRT. So actually it creates a VRT image. So GDAL.autocreate warped VRT. So this actually creates, so instead of storing the entire contents of image, so it just creates a link to that image. So it doesn't, so when you are going to, when you want to save the disk space, so instead of writing an entire image, so you can create a virtual raster. So VRT is a virtual raster. So what it will do, it will just link to some existing image, and the computations will be done on the fly. So instead of doing the computations and writing on the image, what it will do, it will just write in some XML format some metadata about the calculations to be performed on the fly on the image. So just some metadata only will be written in the XML format to the disk. So all the reprojection or calculation, whatever you need will be done in the memory. So this way we are creating a virtual raster. What is the advantage of virtual raster? You are saving the disk space. So with auto create warp VRT, we are just creating a VRT file. So auto create warp VRT takes your old destination dataset, like in which source your source dataset. So our source dataset is old DS name, and none we are passing, like then it will take a source projection system as from our original dataset, and then destination projection system, like we want to convert it to which projection system we want to reproject the image. So actually we want our image old DS to be reprojected to our CRS. So CRS we have created it here. So our original image we want to reproject to UTM 44 north. So actually what happens during this process, some deformation takes place or pixels, new pixels come. So now a resampling technique. On which resampling technique you want to use for reprojection. So that is the fourth argument. So first is your source data set. Then you can pass second argument as none. So if you are passing it none, the source projection system is taken as whatever projection system is available in your file. And next is destination projection system or the reprojection system, in which you want to reproject your image. So you want to reproject to this particular reprojection system. So actually this must be in WKT format. So we are just converting it to the WKT format, crs.export WKT, and then resampling technique used for reprojection. So if we just do this, so it just returns a virtual raster. So this raster, when you write to the disk, it will not be writing the entire array. It will be just writing some XML metadata for processing information only. So the processing will be done on the fly. So when you read this image, so it will read data from some other file and do some computation on the fly and return you results. So you are not writing entire results to the disk. You are just writing some XML information. So now let us visualize these original image and projected image together. So this way you can see that this is slide reprojected image. This was our original image. So when we reproject it, like this. So this way, and now you can even write this image to the disk as well. So this way you can reproject your image, or actually if you don't want to create a VRT, you can just call gdal.reproject also, or even warping also can be done. There is a further function called gdal.warp. So with warp also you can reproject your image. So that's all. This is for today's session. So just a quick recap of what we have done. So today we learned how to stack multiple single bands rasters together to create a false color composite or composite image. So for making this composite, you need to read all the images one by one, and at last you create a single raster with multiple bands and copy these all data one by one to that band. Then we saw how do we subset an image. So subsetting an image can be done using gdal.read as array method and passing in the only extents to which you want to read your extents which needs to be read in your data array. Then we saw how do we resample. Then we saw how do we reproject our image. So thank you very much for attending today's session. Now, if you have any questions, you can just post the questions to the chat box and I will be happy to answer those questions. Thank you very much.